Given doping concentrations and intrinsic carrier concentration, how do we calculate the carrier concentrations of N and P? That's what we're going to see in this video. And we know the relationship between these carrier concentrations N and P with respect to the doping concentrations is given by charge neutrality equation, which is Nd plus P is equal to Na minus plus N, where the left side represents the total positive charge and right side represents the total negative charge inside the semiconductor. Now we know that Nd plus is actually related to the doping concentration by alpha D times Nd, where Nd is the doping concentration and Nd plus is the ionized doping concentration, and alpha D basically represents the percentage of dopants which are ionized. And similarly, we can write Na minus is equal to alpha A times Na, where Na is the acceptor doping concentration, Na minus is the ionized acceptor doping concentration, and alpha A represents the percentage of acceptor dopants which are ionized. Now for simplicity, we're going to assume that alpha A and alpha D are 1, so that we can write Nd plus is equal to Nd and Na minus is equal to Na. So let me rewrite this expression. We can say Nd plus P is equal to Na plus N. This is the first equation that we have, relationship between the carrier concentrations to the doping concentrations. Now we have another equation which represents the relationship between the carrier concentrations N and P with respect to the intrinsic carrier concentration. And this equation is a result of mass action law. And now, having these two equations, we are assuming that we are given the values of the doping. Let's say this is Nd, Na is known, and even the Ni, the intrinsic carrier concentration, is also known. Now the question is finding N and P from these two equations. So we have two unknowns and we have two equations. It's a straightforward thing to find the values of these N and P. So now to start with, let me take and find the value for N. So in that case, I'm going to take P value from the second equation and substitute that in the first equation. So I have Nd plus P from second equation would be Ni square over N. So substituting that here, Ni square over N is equal to Na plus N. We can rewrite this as Nd times N plus Ni square is equal to Na times N plus N square. We can further rewrite this N square minus of Nd minus Na times N minus Na square is equal to 0. This looks like a standard second order quadratic equation. So we know how to write the roots for this, where N is equal to Nd minus Na plus or minus square root of Nd minus Na whole square plus 4Ni square whole divided by 2. I've used minus b plus or minus square root of b square minus 4ac over 2a formula to find this root. And now we can see from here that the minus sign here doesn't make any sense, because the second term would be higher compared to the first term, which means the resultant for n would be negative if we take this negative sign here. And we cannot have carrier concentration to be negative. So that's why this minus is meaningless in this case. So we are going to continue with only plus. So I can rewrite this expression for N as Nd minus Na over 2 plus, and I'm taking Nd minus Na common from this second term, over 2 square root of 1 plus 2Ni over Nd minus Na whole square. So now we have this electron concentration N. Now we can do some assumption where Nd minus Na, let's say, is far greater than Ni, then we can say this second term would be close to 0, and we can neglect this. In that case, the electron concentration N would be equal to Nd minus Na. And once we know the electron concentration, by using the mass action law here, the second equation, we can find what is the whole concentration, which is equal to Ni square over the electron concentration, which is Nd minus Na. So now we know how to calculate the electron concentration and hole concentration given Nd minus Na is positive, which means Nd is greater than Na. And now let us find out for the other case where Na minus Nd is positive. Let me substitute the value of n from second equation into first equation. So we will end up with nd plus p is equal to na plus ni square over p. And we can rewrite this expression to be nd times p plus p square is equal to na times p plus ni square. We can rewrite this expression as p square minus of na minus nd times p minus ni square is equal to 0. Now we know how to find the roots of this equation for p, where p is equal to na minus nd divided by 2 plus na minus nd over 2 times square root of 1 plus 2ni over na minus nd whole square. This is very similar to the equation that we got for n, just that nd minus na is substituted by na minus nd. And similarly here we have neglected the minus sign, so we are directly writing the plus sign, because minus sign would give us a negative number for whole concentration, which doesn't make any sense. So now again we are taking the same assumption where na minus nd is far greater than ni. In that case we can take the second term inside the square root to be close to 0. Then we can say the whole concentration P is given by Na minus Nd, and the electron concentration from mass action law we can write it as Ni square over the whole concentration, which is Na minus Nd. So now we have the equations on how to find the carrier concentrations for electrons and holes. Now let us look at some special cases where, let's say we have a n-type semiconductor, in which case I'm assuming Na is 0 and Nd is present where Nd is far greater than Ni. In that case I can use this expression that we have here where n is equal to Nd, and we are satisfying Nd minus Na far greater than Ni, the assumption we did here, saying that Nd is far greater than Ni, so that we can take n is equal to Nd and P is equal to Ni square over Nd. And now let us look at for the p-type semiconductor, where we say Nd is equal to 0 and we have Na which is far greater than Ni. In that case we can write P is equal to Na, and we can say n is equal to Ni square over Na. So this is another important set of equations which tells us directly the whole concentration and electron concentration in a p-type semiconductor. We have seen a lot of equations, so let me quickly summarize on situations where you can use these equations. Let me take an intrinsic semiconductor. I'm going to dope this intrinsic semiconductor with pentavalent impurities, where the doping concentration I'm choosing is Nd. Then we have this piece of semiconductor which would be n-type semiconductor. Now assuming that Nd is far greater than Ni, the intrinsic carrier concentration, then we can say the electron concentration in this semiconductor material is equal to N is equal to Nd, and we can say the whole concentration is Ni square over Nd. And this is a very important condition to remember. A lot of people usually don't look at this and directly use this expression. Unless this equation is satisfied or relationship is satisfied, you cannot use these expressions. Now let me take another case where I'm taking the same intrinsic semiconductor and doping it with a trivalent impurity, where the concentration I'm assuming is Na. In that case we have a semiconductor. It would be a p-type semiconductor, and we are also assuming that where Na is far greater than Ni, so that we can write the whole concentration in this semiconductor is Na, and electron concentration would be Ni square over Na. And then we have other cases where, let's say we have this n-type semiconductor, and what if we choose to dope this n-type semiconductor with trivalent? When we try to dope this semiconductor with trivalent, let's say the doping concentration is Na, and let me assume the example we are looking at the top of this line is a separate case compared to the bottom one. So let's not relate NdNa from top example to the bottom one. So now, having said we are doping this n-type semiconductor material with Na, where I'm taking this piece of semiconductor, we are getting The type of the semiconductor depends on the relationship between Na and Nd. So I'm taking now where Na is greater than Nd, and we are also saying Na minus Nd is far greater than Ni. In that case, this semiconductor would be a p-type semiconductor. For this p-type semiconductor, we can write the whole concentration of the semiconductor would be equal to Na minus Nd, and electron concentration would be Ni square over Na minus Nd. And this kind of doping that we are doing on top of already some doping done, where this doping we are doing is opposite to that of the doping we did before. This is called compensated doping. And now similarly, we have a situation where this p-type material can also be doped with a pentavalent with a doping concentration of, let's say, Nd, where we'll get a semiconductor material which has both the kinds of doping, where let me assume that Nd is greater than Na. In that case, we will get Nd minus Na. Let me assume this is far greater than Ni. In that case, this semiconductor would be N-type semiconductor. And the doping that we are doing is actually called compensated doping. In that case, we can say the electron concentration in the semiconductor material would be Nd minus Na, and P would be equal to Ni square over Nd minus Na. So if we have these different situations, then you will be first looking at the condition that we discussed, and then would be using these formulas to calculate the carrier concentrations. Most of the time, the dopings that we do are usually compensated doping practically.